Okay? The size and shape of the particles may increase the ability of the attraction to create solids or liquids or something, and not gases. And then the strength of attraction can, if it's a stronger attraction, would attract smaller molecules to each other, forming solids or liquids. So all these interplay. They're all working at the same time. Got it? Okay? As a result, then, methane is about the same size as a water molecule. It's about the same size, about the same mass. This is about, let's see, 12 and then 4, that'd be 16, okay, AMU for a methane molecule. Water's about 18 AMU. About the same size. Methane's not a liquid at room temperature and pressure. In fact, you have to get it really, really cold to be a liquid. Like 200 Fahrenheit or 100 and something degrees C. But water's a liquid right here in the room. What's the difference between these two? If I have the same amount of pressure, the same amount of temperature, the same value of temperature for a sample of methane and a sample of water, why would this one be, when it's about the same size, why would this one be a liquid and this one be a gas? Nobody knows. No? They're about the same size. Why would this be a gas and this be a liquid for the most part? Huh? If they have the same temperature, they're moving about the same. If they have the same temperature and they're about the same size, then how fast they're moving is going to be about the same. Okay, the molecule doesn't have electronegativity, but they have polarity. Polarity is the result of electronegativity. Okay? Which one's polar? H2O is polar. So the attraction between one water molecule and another is what? Greater than this one. That's what makes this a liquid and that one a gas. Okay? This tends to be a gas at room temperature and pressure. This tends to be a liquid at room temperature and pressure. What's the difference? They're the same structure. There's no difference in the strength of attraction. They're made of the same stuff. Size. There's more places along this long molecule for that density shift in electrons to occur. Does that make sense? This tends to be a solid. Or would this be a solid instead of a liquid or a gas? Huh? Size is bigger. There's more places for those electron density shifts to occur and get more attraction. Yep. Sure. This tends to be a liquid, while this tends to be a gas. What is the difference? Huh? What would cause this which one has the most attraction? Okay, well what would cause the greater attraction? This part right here is polar, like the water molecule is polar. Okay, water molecules are HOH, right? And this is just the OH part of it. Well, we got polarity there, don't we? See what I'm saying? There's a great deal of electronegativity difference between oxygen and hydrogen. And we had to figure that out. The electronegativity of oxygen is about, 3.5? Hydrogen is about 2. That's a lot of electronegativity difference. This is a really polar structure. Do you remember how to calculate that? Yes or no? Do I need to go back and review that whole unit? Yeah, it's the arrangement. Remember, electronegativity, the greater the electronegativity between two atoms in a covalent bond, the greater likelihood you're going to have a polar molecule. Well, this is a very polar grouping, even when it's tied into an oxygen, a carbon here. Okay? Which one of these is going to have the highest boiling temperature? Why?
Because there's two OH.
Uh-huh.
So the attraction will be stronger, so it'll be harder to break.
You got it. Y'all understand his explanation? If they're more strongly attracted, it's harder to get them to boil. It's also harder to get them to melt, or easier to get them to freeze. Does that make sense? If they're held together more tightly by their structure, it's easier to get them to freeze, harder to get them to melt. Does that make sense? That's that structure, building a building out of these structural particles. Okay? NH3, or an NH2 grouping, okay, is also a polar grouping, but it's not as strong as the OH. The electronegativity difference between nitrogen and hydrogen is less than the electronegativity difference between oxygen and hydrogen. So this is more polar, and this is less polar. But they're still polar. Okay? Which one of these is going to be a liquid, which one's going to be a gas at room temperature and pressure? Okay? Because why? OH is more polar than NH2 is. They're still both polar, but this one has more strength of attraction between this structure and another one like it than this one does. Does that make sense? So all that stuff we try to figure out how to predict when you had a polar molecule, it comes down, it doesn't just come down to this, but one of the things it comes down to is how do you make it a solid, liquid, or gas? Or is it going to be a solid, liquid, or gas? And at what temperature? Does that make sense to everybody? Who's lost? If you don't have the guts to raise your hand, you deserve to fail the test. Who's lost? Okay, I'm trying to get you to answer up. All right? I want to make sure you understand. Yes. The more polar the structure is, the stronger the attraction between that structure and another one. Okay? So if I have CH3, CH2, and I'm going to draw it out like this, okay, so that I can show there are a couple of lone pairs over here. All right? So this structure And this is going to be more positive because the electrons are being pulled that way. So this is kind of partially positive and partially negative. Okay? And so if I have another one of these structures, this is also a partially positive and partially negative. Okay? So there's a what's called a hydrogen bond between this end of this part of the structure and this part of this structure. And the strength of that attraction tends to get them to stick together. If they tend to stick together, they tend to be more liquid or solid than otherwise. That's tendency, doesn't mean it's going to happen. Okay? It just means it's making it happen more often. Okay? Just because one football team is a better football team than another doesn't mean that on any given Sunday that team doesn't lose. I mean, if you're a football fan, you understand that probably. Okay? If you're not a football fan, you might not get it. Any given Sunday, it's a phrase in football jargon. No, you don't get it? You understand? You understand? Okay. Got it. All right. All right? Just because one person is a better player than another player doesn't mean they can't lose. Right? So, sometimes people just get lucky. Okay? Things happen. Well, the same is true here. Tendencies don't mean it's always going to happen. Tendencies means it's more likely to happen. And that's what science deals in, especially chemistry. Tendencies. Okay? We can make predictions based on tendencies. All right? All right. Let's see. Of these two structures right here, which one is more likely to be a solid at room temperature and pressure? Why? Well, you just know. But I want to know why. We're doing modeling here. We're in chemistry. We've got to figure out what's going on with the structural particles to make it work that way. Why? Well, you said polar? H2O is polar.
They have a higher, or the difference is greater between them on the electronegativity.
Okay, you could look at it that way. What he looked at was the electronegativity chart. And the difference between sodium and chlorine is huge compared to oxygen and hydrogen. But there's really a deeper level of understanding of that. In that sodium, it tends to be a completely separate charged particle. Okay, and chlorine is a completely separate charged particle. Water molecules, this is our lone pairs up here, okay, are polar. Polar attractions are not between one water molecule and the next. Between one water molecule and the next, the polar attractions between one water molecule and the next is not as strong as a completely charged particle. Remember, this is a partially charged particle, not a completely charged particle. Okay? Partial charges are not as strong as complete charges, like between sodium and chlorine.